Right, we'll get started in just a minute or so. Thank you all for being here. Thank the panelists and the co-organizers. I'm Jack Hay from NASA headquarters. I'm one of the organizers and the moderator for the Explorer at 60 years of viewing the Earth from space session, and very pleased to have the panel, distinguished panel that we have here for today. What I will do is do very brief introductions of all the panelists, turn it over to them to go through their talks. We've got, I think, 17 minutes allocated for each of them. The hope is that unless there's really burning questions that people feel they absolutely need to have answered right after the talk, we'll kind of move through them sequentially, and then if we can keep everyone on schedule, which is one of the things that I guess I'm supposed to be doing that I'm not normally very good at, we'll have close to a half hour for discussion at the end, and start out if there's any questions that the panelists or co-organizers have for that, but then to really try to open it up. And there's a microphone there, so when it comes time, just can line up and we'll open up the time for discussion. And so I'll start off with some very brief introductions, and sort of the emphasis will be, as much as I can restrain myself, on very brief, because the panelists here have so much experience and are so distinguished that it would be very easy to spend a fair amount of time hearing about them, but I think it's better that you get to hear from them. So I will try to be very brief, and I'll just go through, do all the introductions at once in order, and then try to get out of the way. So first up is Thomas Zurbuchen, the Associate Administrator for Science at NASA. He's been in that position for a little over a year. Before that, he was a professor of space science and aerospace engineering at the University of Michigan, where he helped found the Center for Entrepreneurship. He's been was an investigator involved in several NASA science missions, Messenger, ACE, Ulysses, research in solar and heliospheric physics, experimental space research, space systems, innovation, and entrepreneurship. He also chaired a committee for the National Academy of Sciences for their study, Achieving Science with CubeSats, Thinking Inside the Box, that came out last year. He's a winner of the Presidential Early Career Award for Science and Engineering in 2004, a PhD from the University of Bern. Next will be Bill Lapenta. Bill's director of NOAA's National Centers for Environmental Prediction, where he oversees planning, science and technology, operational responsibilities for NCEP's 9 national centers. Before he got to NOAA in 2008, Bill worked at NASA for about 20 years at the Marshall Space Flight Center, where he served as deputy manager for the Science and Exploration Research Office. He also spent a number of years as the principal investigator and chief scientist for NASA's Short-Term Prediction Research and Transition, or SPORT Center, that focused on transitioning NASA Earth science assets into the National Weather Service weather forecast offices in the southern U.S. Bill has a PhD from Florida State University. Then comes Marshall Shepard. Marshall is the Georgia Athletic Association Distinguished Professor, Associate Head of the Geography Department, and the Director of the Program for Atmospheric Sciences at the University of Georgia. He's been there since 2006. Before that, he was a research scientist at NASA's Goddard Space Flight Center, and also was a deputy project scientist for the Global Precipitation Measurement mission. Marshall's a past president of, I guess I can say it here, the American Meteorological Society. He's received other awards from the AMS. He's a TV host. He hosts the Weather Geeks show on the Weather Channel. He also was a winner of the Presidential Early Career Award for Scientific Research. His PhD is from Florida State University. Then comes Susan Avery, President Emerita of Woods Hole Oceanographic Institution. She was president there from 2008 to 2015. Before that was a faculty member, administrator at the University of Colorado in Boulder, where she's now a professor emerita, and she did a variety of things there, director of the Ceres Institute, vice chancellor for research, dean provost, executive vice chancellor for academic affairs. She's also a former AMS president. Finally, Jim Russell from Hampton University. Jim's an endowed professor at Hampton's Department of Atmospheric and Planetary Sciences. He's the co-director and co-founder of the Center for Atmospheric Science. Before being at Hampton, he was a research scientist and branch head for 2 different branches in the Atmospheric Science Division at NASA Langley. Jim has a long history of being an instrument PI on NASA satellite missions, including the co-PI on the LIMS instrument that flew on Nimbus 7, the principal investigator for HALO on UARS, for SABRE on Timed, and the PI for, on the AIM mission that flies as well. He works in atmospheric science, remote sensing, satellite data analysis, both for what we would consider as earth science and heliospheric science. And so if you caught it, his experience as a PI is for missions that span 5 decades, from the 70s, 80s, 90s, aughts, and 10s. And he looks way too young for that. And his PhD is in aeronomy from the University of Michigan. So with that, I'll turn it over to Thomas, and we may have some interesting things when we change between Mac and PC and stuff, so hang with us, we'll get through it.
Well, I'm really glad to be leading off here because I'm looking forward to hearing all these talks that are given right after me. Of course, I'm leading off with the viewpoint in mind of NASA science overall and the importance of this particular mission for everything we do today, including Earth science. You see up here that stern-looking eagle with Explorer 1, the body, and of other missions there, really indicative of our pride and excitement as we come up to this anniversary. And also showing how these missions really connect to each other. That's really the theme that I want to talk to you about, really talking about the legacy that was created from it, but also how so often the element of surprise is so important in what we do, and kind of planning to do the right thing, to be open to take advantage of the surprises that are going to come to us. Now I'm trying to figure out which button to push. If you had to guess which one it is.
Probably this one.
Okay. No, this is another mouse. Oh, we found it, so this one. So, of course, the day was January 31st in 1958, and around kind of 11 p.m. That day, Explorer 1 launched just a little bit after Sputnik, very motivated by actually wanting to go to space after, unfortunately, being beat in this very political, very visible competition to space. And so basically, Explorer 1, unlike Sputnik, of course, carried a science payload, a payload that was developed at JPL by Dr. Pickering, and then, basically launched up there, and to everybody's surprise, lots of preparation, but to everybody's surprise, what happened is that as this mission went above the atmosphere, of course, the radiation increased only to drop immediately in a way that, the uninitiated person, of course, would have guessed that, hey, there's no radiation there. Van and his friends and colleagues over there, of course, immediately recognized that the reason this count rate dropped so quickly is because the instrument was choking, because there was so much radiation up there that the instrument, as designed, could not keep up with it. And so for me, Van Allen, having known many of his people, we overlapped a tiny little bit in the community, as being an inspiration, just because of not only what he did there, but how, of course, he shaped what came afterwards, like how the many missions that he was involved in. Certainly, one of the most enthralling things about human life is the recognition that we live in what, for practical purposes, is a universe without bounds. Yes, above the atmosphere, stuff is happening, and it's absolutely exciting science that not only relates to our home, our life, but relates to the universe around us. The universe is about many more things that we would have immediately guessed if we looked at our immediate neighborhood. And that's in many ways what Explorer 1 did, really opened that door to that universe without bounds. Of course, we're learning a lot more from this, and this is a mission that carries man's name. And kind of what's indicated here, what's shown here is the result of March 2017 coronal mass ejection. March 17, 2015 coronal mass ejection that struck this outermost belt. And what you see here is electrons that are, of course, modeled here that are drifting around this magnetic field, something that was observed by these missions that, of course, are out there and really doing breakthrough science, teaching us a lot about these belts, which, of course, carry man's name. I remember being on the Hill, kind of young, and kind of talking to congressman that was actually in the same state where Van worked. I basically said, "Do you ever realize that there's parts of the sky that have the name of your faculty there at this university?" That's amazing. There's not many states like that. So that's kind of in memory of Van Allen and the amazing science that he has done. What's really surprising, though, is that just a few years later, TIROS 1 launched. And so really, kind of this, as this door was opened, many more things happened. And of course, it took the first TV image of the Earth from space and really quickly was turned to use. I mean, to me, what's really remarkable here is that the kind of forecasting elements that were related to TIROS 1, of course, were starting to develop really quickly. Within years of this first time kind of going through that important boundary, of course, one of the key elements is this typhoon over Brisbane, Australia, which it looked at and observed. Where are we today? I mean, so for me, this is one image. It's a still. If Mike Freilich was up here, this thing would move, and you know, Mike would excite you with all his words that he has, you know. But so for me, what I love about this image, of course, is it shows, first of all, three names, you know, Katia, Irma, and Jose, that were these hurricanes there. It also shows the data that are available, both looking at the clouds, but also at the lights from, you know, civilization that is there. And it's kind of the multi-sensors that are being used to integrate such a view of this complex system, Earth, is really started the first time we launched into space, but is being developed as we go forward, both to really further the research. There's a lot of things we don't know yet, that this is a really important system worthy of our exploration, but at the same time, every time we learn about something about our Earth, like about the physics of these storms, we learn with our agency partners, NOAA and others, we learn how to take that knowledge and turn it to immediate use, really protecting and improving life on Earth. And so to me, that's one of the key legacies about this. The Planetary, first Planetary mission, of course, is in 1962, Mariner 2. Of course, you don't go to all the talks that I'm giving, except the people I'm forcing to, apparently. No, I see some faces, but what happened there, of course, Mariner 2 is a mission that was launched in August 27th, 1962, and was heading towards Venus. What's exciting to me, though, in addition to the amazing Venus science that happened from that and the subsequent missions, is that an instrument that it carried, again built by JPL and actually MIT, actually looked at solar wind and basically proved that Parker's hypothesis of a steady solar wind, a supersonic solar wind that really filled space, was in fact true. And so again, of course, it confirmed that Venus was hot, but on the way made these amazing, surprising observations that, again, shape what we today call heliophysics. Again, starting with this immediate recognition that we can go beyond. What happened in looking at planetary sciences, of course, takes your breath away if you look at these images. This is, of course, from Voyager, looking at Jupiter, which it was designed to do, but then recognizing that, hey, there's bodies around Jupiter that are way more exciting than any of the imaginations that we would have. This body, of course, being Europa, that has oceans under the surface, as the, recognized by a series of measurements, including magnetic field measurements and otherwise, and basically recognizing that this ocean actually has more water than the oceans here on Earth. And so for me, it's these worlds that we're now losing sleep over, because of the fact that there's a number of questions that relate to these worlds that actually are simple questions like, is there life elsewhere? Questions like that, we really are puzzling about how we could answer them. And of course, we're developing missions that take the best of what we know about these questions and send them out there knowing real well that there's surprises waiting for us. Another one that I want to talk about is, of course, one that just came to an end, Cassini. Of course, Cassini, going around the most impressive, majestic planet we could imagine, right, with these rings and just the physics of the planet itself. But then you, again, flew by this other world, and I'll never forget the time when I was walking out of the office, and somebody across the hallway, who was the PI of that mass spec instrument, Hunter Wade, basically said, look, you can't believe what I just saw. I said, look, there's like water and organics coming out of this thing. And I'm like, look, are you sure your instrument is not crazy, right? But like, of course, what he was observing is Enceladus and the amazing world that is there. Again, a surprise beyond belief, but one that happens when you look at this cosmos, this universe that is unlocked when we get above the atmosphere. And then astrophysics, of course, with Explorer 11 in 61, was looking at gamma rays, the observations, of course, that are not really accessible on the ground because of the fact that there's a kilogram per square centimeter between us and the universe that kind of thankfully protects us from a lot of the stuff that's coming down from the universe. And basically looking at this, of course, learned about the abundance of these sources in the universe. But as we look at this today, of course, this being a combination of Chandra Chandra data and Hubble, we basically recognize that this energetic universe, is full of some of the weirdest objects. Some of them that that come out of calculations that you can do in school, but sometimes you worry about whether they're correct. Well, one of them, of course, is kind of signified there just as a chart at the bottom right, which is an event happening in August 17th this year, where two neutron stars were observed to collapse onto each other and merge, and basically, of course, that was observed first with a totally new asset built by the National Science Foundation and its partners, LIGO, using the gravitational waves, but then we observed it with many, many different assets in space and from the ground. Really, in many ways, the home run event for astrophysics, in a sense that it proved that these events actually are there, produce short gamma ray bursts, short duration gamma ray bursts, which is one of the pulses that was out there. But most importantly, after this convergence, creates all kinds of metals that we can now buy jewelry from, platinum, gold. All these things are out there and are created in these cosmic collisions that we really best observe on the outside of the atmosphere. And again, ready for a surprise. It's a surprise that happens, but we're ready because we have the assets that actually can take advantage of that. Michelle, who did a number of these slides, I think just beautiful slides, took a screen capture from this URL. And it's, if you get, every once in a while you worry about things, go look at this. It will open your mind, it will inspire you. It's exoplanets.nasa.gov as of just a few days ago. Here's the numbers that are there at 3,500 and change exoplanets confirmed, another almost 5,000 candidates that are out there, and the clock is ticking up, the kind of near terrestrial type of things getting closer to the thousands, right? The kind of really, this is the universe that we look at today. Did we believe that there are planets elsewhere? Well, the models kind of that should likely occur? Well, the likelihood of these planets is about a factor of 10 higher than I learned in school. Now, I don't know whether my teachers just didn't know any better or whether the whole community was really off. I would guess it's the latter, because once we look at the sky, we're surprised by what we see there. Once we look at the sky, both from the ground, so often in these observations, from the ground and from space together, we learn about the universe and its wonder, the boundless wonders that come when you get out there, really, again, unlocked by this. Of course, this is another thing I lose sleep over. No. This is another telescope that we're getting ready to launch, and like they always say, the Mars is the 7 minutes of terror. Well, talk about 6 months of terror. That's about how long it takes to set up that amazing telescope, which will break all the records that we've built, both in size. This thing is 6.5 meters in diameter, and the thermal protection system are the area of a tennis court and very flimsy when you go stand next to them. And of course, it's exactly what it should be. This is the kind of next generation telescope that allows us to peer into the first galaxies, the early universe. And what will we see? We'll see some things we expect, but most importantly, we'll be surprised, because that's what always happens when we push the boundaries. And so basically, I could talk about each one of those missions, and I will not. Some of the ones in bold-faced are the ones that we're working on right now, both in earth science, heliophysics, in astrophysics and planetary sciences. But what I want to leave you with is just the recognition that all of those have a root in that first mission that this session is about. And so we're just really excited to be celebrating that anniversary with you as we get into next year, and I look forward to hearing the next talks. Bill, over to you.
All right. As I said, we're going to try to just go from speaker to speaker and then do discussions and questions at the end. And one thing I neglected to do at the beginning was to introduce the co-organizers, Elsaid Talat from NASA Heliophysics, who's lead scientist, and Harry Sikanik, the director of NOAA NESDA's STARS organization. And they will also help provoke discussion too. So with that, Bill, we'll warn you at 15 minutes, and you should be able to get you out of here because you're on the Mac, right? So
no, I'm on the PC.
You're on the PC. Let's see. Hopefully,
little transition here.
No, that's because you're on this one, so maybe it's. Okay, so,
Yeah, that's totally counterintuitive. Yeah. So I just clicked, because I couldn't find the keyboard. The keyboard was attached to the wrong machine. So I just I started going through everything. So the final thing I found was the mouse. So you have the keyboard. If you use the Mac, you have the keyboard. So you can just use it right there. The keyboard. The keyboard worked on the Mac because I saw it moving on the Mac.
This is you, right? So it's a.
Right. It worked.
You had it.
Okay.
You had it.
Go to 4.
There
That's
it
the
is.
solution.
Okay.
Okay.
Thank you, Jack.
Nobody move.
All right, you can start the clock now. Thanks for your patience, everybody. First of all, I want to thank everyone for taking the time to spend the afternoon with us here. I know you have a lot of other options, but this really is quite an anniversary, and even I'm excited by it. So what I want to do is talk about the use of satellites really today. I'm not going to give you a history about satellites and how they're used in the Weather Service, but really focus on where we are today in terms of the technology available to us and how we use that technology to serve the public and our core customers from the National Weather Service perspective. So within the Weather Service, just a little bit of background, we operate what's called the Weather Ready Nation. And it really is a strategy, an outcome to develop a nation that's ready, responsive, and resilient to high-impact weather. We're not just talking about 65 and sunny on a Sunday afternoon. It really is focused on the information, hazardous weather, and providing stakeholders information they need to make decisions so that people take appropriate actions. And so in 1993, Alan Murphy published a paper that basically said, look, forecasts really don't have any value until somebody takes action based on that information. And so we have really taken that to heart within the National Weather Service. And it is true in the sense that we are really focused on going that last mile, taking all the advances in technologies, whether it's from the observing system, whether it's from the models that we run, and transitioning that into information that people can use and take action on it to protect life and property. And this is just an example of what we call impact-based decision support services, where we're trying to communicate to the customers so that they can communicate to their stakeholders. And this is just an example of a snowstorm in 2013 and one in 2016 in the East Coast, Long Island area. The figure on the left-hand side shows the LIE, what it looked like in 2013, where perhaps our messaging really wasn't very clear or consistent, and perhaps maybe not accurate, compared with 2016, where perhaps we were a little bit more on the ball and communicating more clearly. And the big difference here is that not just the protection, from a health perspective, people getting caught in cars, but the economic impacts of having to forklift people off that road or cars off that road in 2013 for 3 or 4 days, while on the other side in 2016, 12 hours later, you're back in business from an economic perspective. So that's really just an example of IDSS. And so now I'm going to talk about how we use satellite data. And what you have here is just an animation of accumulated snowfall from one of our operational regional models for the latest event that went up through the south into the northeast. And satellite data is an absolute critical part of what we do for numerical weather prediction. It is a foundational piece of the puzzle, and I typically go out and talk about the models themselves, but here I'm talking about the satellite data. And numerical weather prediction is an initial value problem, so you have to have a good handle on what's going on from an atmospheric state perspective. And the use of satellite data from a global observing system perspective is absolutely critical. We've done tests without the use of satellite data in a modeling system, and the skill is dramatically worse. So satellite data has played a very important role and perhaps one of the greatest inventions, that being numerical weather prediction, that we are responsible for in NOAA. And this is just an example of where we're going with the use of satellite data in some of our experimental high-resolution numerical modeling. This is an example of some of the recent wildfires that were going on in the West Coast. We use some parameters from satellites, fire radiative power, to initialize location of fires within the high-resolution experimental runs in the West. And then from that, there's a smoke module in the model that simulates the emissions of smoke and the translation of that smoke within the wind field. But again, it's that satellite data that provides us the information about where those fires are initially, and we incorporate that into the initial conditions of the numerical guidance that plays a critical role in determining where that smoke plume might go. And another important part of the use of satellite data is not just within the initialization of numerical models, but also in the validation and assessment of those models. It's absolutely critical that we understand the phenomena, and satellite data and all the research that has come along with those satellite data has helped us to understand the phenomena better. It allows us to then model it better. Satellite data then allows us to validate and assess the models are doing the right thing. And then you have that natural development cycle between physical understanding, modeling, observations, and it's just an endless cycle. And when I was at NASA, we did observation-driven modeling, Jack, correct? And you taught me that, and so that's what we did at NASA. And so now I'm just going to talk about another couple of applications, and I'm just going to wrap it up. In the National Weather Service, we have a broad scope of service areas, ranging from space weather, we have marine, tropical, we have fire, severe, and I'm just going to give you a couple of examples this afternoon. In my slide deck, there are numerous more examples. And so we are responsible for the civilian space weather prediction, and you talk about a service area where the observations are limited and starved. You know, I thought from an atmospheric perspective, I'm a modeler at heart, I thought we were starved in the atmosphere, the terrestrial atmosphere. And when it comes to space weather, we really have a thin observing system, and we heavily rely on some of the research-based satellites that NASA has launched over the years. We have just launched, from a NOAA perspective, the Discover satellite a couple of years ago. And so these satellite data are absolutely critical to our ability to predict and estimate the intensity of coronal mass injections that are impinging upon the Earth, and then translating that into information in some of our newly implemented operational modeling capabilities to determine what the impacts might be to satellites, to the power grid. But again, without these critical observing systems, I can't imagine where we'd be. But again, just an example of what we do from an operational perspective. And now we're kind of moving into the terrestrial area, and what you'll find is that the forecasters in the National Weather Service are really creative. They're information starved. You know, you think we throw a lot of things at them, but each part of the region, or each part of the continental U.S. and the Alaska and the Pacific region have unique needs. And this is just an example of a total precipitable water product that's developed by Sierra at the request of the Western Region National Weather Service folks, because the atmospheric rivers have a large impact on the hydrologic aspects of the West Coast, also agriculture. So this is an example where satellite products are absolutely critical to the mission of Western Region, and we're using satellite data specifically tailored to meet the needs that they have from an operational perspective. Very responsive. Now we get into a little bit of the GOES, and this is just an example. This is just off the east coast of Florida. This was in October 29, 30 of 2017. And GOES 16 is really exciting. I have to admit that, you know, I'm trying to maintain a level, you know, balanced approach to satellite data. From a modeling perspective, everybody wants to know, well, how much impact does my satellite data or my remote sensing product have on the quality of the guidance that you provide? And so I keep an objective perspective, because it's really the accumulation of all those data together that matters to me most. However, I will say that GOES 16 has even excited me. And Thomas, you were talking about this earlier. When you showed the 3 hurricanes, my heart rate went up. Because it really is exciting in terms of some of the things that we're seeing now, just in its infancy with GOES 16, that higher vertical resolution, some of the new channels, and that temporal resolution, I should say with the horizontal resolution. We're seeing things, quite frankly, from an operational perspective that we haven't seen before, and what we see from a research perspective is going to be just absolutely outstanding. And so, you know, we saw the 3 hurricanes a little while ago, and I'm going to kind of wrap it up with the hurricanes, because this summer, or this Atlantic hurricane season, was very busy, as everybody knows. And as the director of NCEP, I have overall responsibility of the Hurricane Center. And for the last several years, it's been a relatively quiet Atlantic season, although we have, you know, Matthew and Joaquin. So, you know, on that Wednesday before Harvey, I forget what day it was, but I decided to go down to the Hurricane Center and just observe how the Hurricane Center operates during a landfalling hurricane. And so I drove down, I think I flew down, I should say, on a Wednesday afternoon, got onto the floor Thursday morning, and that's when Harvey was undergoing rapid intensification. And I was on the floor with the forecasters, just staying out of their way, and watching how they operated. And the Hurricane Center folks, you know, the hurricane specialists are kind of a staunch group. They really don't like committing or saying things that give the impression that they really like something. You know, they're kind of, they maintain that level perspective. But I'll have to say that the hurricane specialists were very excited about looking at GO-16. We had the 30-second imagery up. I was taking videos with my cell phone and showing it back to Louis back in DC. And it was just absolutely amazing to be on the floor watching the 30-second imagery with GO-16 during Harvey. And the thing you had to realize is that, we had loops up. And you had to sit back and realize that what you're looking at was maybe only an hour and a half in length. Typically, you'd have a loop that's 3 or 6 hours. But the amount of mass and water that was being rotating around in that hurricane, as visualized by that satellite, was just absolutely amazing. And it was a very profound moment, not just because of what the people did in terms of the prediction of the hurricane, but the technology that we have available to us now is just very exciting. And then I just want to end to talk about, just perspectives, right? When I was a grad student in the undergrad, in the late 70s, early 80s, we had our satellite imagery on Difax charts. That's the way it was. And I can still remember standing in the map room at State University of New York in Oneonta and looking at satellite imagery on these Difax maps. And, look at where we are today. And all of the satellite data, we use operational, we use research-based. The physical understanding that the research community gains from using satellite data leads to the improvement and development of the models that provide us that predictive capability. And then it helps us assess and validate those models, which is extremely important. And then the role that the satellite data play in that constant evolution of physical understanding, model development, validation, and on and on and on is just truly exciting. So I just want to say that from a Weather Service perspective, we love and absolutely rely on these satellite data. The forecasters are really creative. We're just starting to see things we've never seen before in these animations, gravity waves. With Hurricane Harvey, you could see the vortices in the eye, and when it was approaching land, you could see them in the radar data. Again, just things we've never seen before, and the expectations are just through the roof. So with that, I'm going to turn it over to Jack, and thank you very much for your time.
Right, yeah, so now we get to, okay, I guess he's got, just have to.
That last image, what was that?
That was Maria.
What was that island?
Oh, it was Puerto Rico.
Puerto Rico. And so it turned, so.
What's that?
So it turned.
I think you've got just a little while. It's the second round.
It is with the X's.
Yeah.
I thought around was up there, just on the other island.
Okay.
It's really
And then take me a minute to reset the timer here.
That's the thing. When I was on the floor watching this thing, watching Harvey, it was just unbelievable.
Oh. So next up is Marshall Shepard.
Thank you, Jack. So I'm here to, as a scientist, to place the context of this particular session because we're reflecting on the importance of a particular satellite that sort of spearheaded observations. But I like to place these in the context that really this piece of machinery and metal in orbit is really about us. And so I'm going to present on two applications of satellite remote sensing to the hydroclimate. And when you hear the word hydroclimate, just think water cycle and how we're using satellite technology to study aspects of how our water cycle is changing. And so I'm going to put on my academic hat and talk about some of the research that has been enabled by NASA to study the water cycle, which we all depend on for life on the planet. So actually, Thomas and I shared a stage a few months ago at the Air and Space Museum and the IMAX Theater, and in that talk, I actually made this statement here, which is that if you go far enough into space, Earth looks like a star. And in fact, what you're looking at there, and you can't see it carefully, so I highlighted it in the box, that's what we look like from the surface of Mars. And so from the vantage point of Mars, we look like any other star in the sky, but in fact, we're not. We're a planet bustling with life, with water, with cryosphere and whatnot. And so it's important for us to understand this water cycle process that sustains and enables life on the planet. NASA actually approaches Earth as a study from a systems perspective, and you cannot study a system perspective without the unique vantage point that space provides. When we're studying oceans that Susan's going to talk about, or the atmosphere or weather that I talk about, or climate variability, Earth's surface interior, the carbon cycle, those work together as an integrated system, and a satellite vantage point in space and time enables us to understand these various processes. So I don't have a chart as robust as what Thomas showed us, but this is a look at sort of the Earth science missions at some point in their life cycle. At other points in NASA's history, we have launched satellites to study the water cycle. And though the names on this chart may have changed at time, they're GRACE, TRIM, GPM, SMAP. All types of satellites have been placed in orbit in order for us to better understand what's happening in our water cycle, from weather to floods to soil moisture. And so that's what I want to talk about today. So I picked two topics that are part of my research portfolio to try to give you some understanding of how we enable basic science, but also advanced applications for living on the planet as well. I want to acknowledge my co-author, Joe Santinello, as well, who's done some work with me on this particular project, the Brown Ocean. If you Google the Brown Ocean, we have a Wikipedia page, so someone else felt it was actually important enough to place a Wikipedia page. This is the concept that many of those hurricanes that you just saw Bill talk about, when making landfall, can actually maintain their strength. We think of hurricanes as weakening or intensifying as they move over land, but there are several opportunities or cases where storms move over land and intensify. So let me give you some context for why that's important. You can't read all of the statistics here, but this is the 2017 hurricane season. And we already have accounted for the fact that $202 billion in damage is likely the cost of the 2017 hurricane season alone. Hurricane Harvey was a big part of that. One of the things that we must remember about Hurricane Harvey is much of the damage came after the storm weakened from a hurricane to a tropical storm and sat there and rained for days. And so this notion of understanding the danger and impact of a hurricane after it makes landfall has been an oft understudied topic, and one that I got very interested in a few years ago with one of my PhD students. So I'm not going to stick to the motivation in the interest of time, but just know that Dr. Teresa Anderson and I, who's one of my former PhD students, we got very interested in, if you look at the bottom right there was a tropical storm that moved into Texas and Oklahoma and had an eye sitting over Oklahoma, and you can see it there in the radar. It looked like a full-fledged tropical system, Tropical Storm Erin. And we were curious about that. If you look to the top right, don't worry about what that is. That's a look at the previous 3 months or so worth of rainfall as measured from a tropical rainfall measuring mission-based product. I see Bob Adler in the back there. I think it's actually one of his products. Looking at the antecedent moisture. And what that shows us is that there was plenty of moisture sitting in Texas and Oklahoma. This tropical storm traversed right over that moisture, and it thought it was still over the ocean. And so based on sort of the physical processes that power these storms, the wet soil, we came up with this concept of the brown ocean, and we became curious about how often does that really happen? We know that certainly tropical storms can intensify or maintain their strength through things like extratropical transition, upstream troughs, some of the more meteorological processes, but can wet soil fuel a hurricane? Because at the end of the day, hurricanes get their energy from evaporative water that recondenses in the atmosphere. So that's what, through a NASA-funded fellowship, my student, Teresa Anderson, started looking into this. And lo and behold, what she found over this 30 or 40-year period is that there are over 200 or so cases, and we're very conservative in how we partition these cases out, of storms that actually maintain or intensify when they move over land. Now, many of those were just related to the more common meteorological process of extratropical transition, like Sandy. Hurricane Sandy did it. It goes from a storm getting its energy from the ocean to a storm that's getting its energy from differences in air masses. And so that's what we mean by extratropical transition. But there were this class of storms, these what we call brown ocean storms, that are intensifying or maintaining their strength because of evaporation over wet soil. And so some of the findings, these tropical cyclone maintenance storms, that's what we call them, they basically occur in situations where the atmosphere is mimicking an ocean, what we call a barotropic environment, not a lot of wind shear. You have to have a certain threshold of latent heating. And why that's important, we found, is that the extended rainfall associated with these brown ocean storms can be a flood hazard inland as they move in. So this is something that's just not some esoteric scientific research. It has a real application to someone that's trying to understand a flood situation that may come from a Harvey. Now here's an example. I've taken data from soil moisture data from NASA. We got this from NASA Marshall Space Flight Center. And look at what you see in Texas. There's dry soil. That's what the red colors represent. Then you see thunderstorms coming along, and watch the soil become more yellow and green. That means the soil is moistening up over a sequence of weeks. And that's what we see. We are superimposing some rainfall data. And here comes Tropical Storm Bill in 2015. Watch what happens as Bill moves over that now pre-moistened soil, the brown ocean, if you will. It maintained its structure quite nicely. And through work that's now being funded by Dave Considine's program at NASA MAP, we're actually looking into storms like this from a modeling perspective to understand the physics behind how a storm like Tropical Storm Bill can feed off the ocean. Now, as Hurricane Harvey, which we just heard about, was happening, people were starting to tweet me and ask me, is Hurricane Harvey producing a brown ocean effect? Hurricane Harvey was a very significant storm. It produced, if you can see on the top left, that's the pre-Hurricane Harvey rainfall there on the circle, and then afterwards. Hurricane Harvey came along, really moistened up the soil to the east of Houston. Here's data from the SMAP. You see the blue colors, that's wet soil as measured by the SMAP satellite. So there's plenty of moisture in the soil. So people were asking, was Hurricane Harvey creating a situation where it was feeding on itself from soil moisture in Louisiana? The answer to that is we don't know. But that's certainly one of the things that we're going to be studying in the next couple of years through our MAP project. Now in my last, I'm going to kind of skip forward, my last what do I have here? 6 minutes, perfect timing. I want to shift gears, so just go along with me as I shift gears and talk about another research area that my group has been involved with over the years. This was one of the pieces of work that I was fortunate enough to be acknowledged for my PCASE award, along with Thomas several years ago, I guess 2004 now. I've been doing a lot of work on how urban environments can impact weather and climate. That's kind of my sort of bread and butter research topic. Many of that started at my time at NASA Goddard. Here in this picture on the top left, that's the city of Atlanta, downtown Atlanta, and a fog deck. But notice that that little sliver there along the urban corridor is where the buildings and the urban surfaces are heating because of the urban heat island and removing the clouds. So that's an example of the atmosphere, the land surface talking to the atmosphere, communicating with the atmosphere and clearing. And I see Jim Iron sitting in the office, so in the audience, so he'll appreciate this, that I'm showing Landsat data, because Landsat has been another valuable workhorse in NASA's and USGS's fleet, many years of sustained measurements of land cover and land use change. So you see the urban land cover there of Atlanta, and you see the urban heat island signature as measured by a thermal instrument out of Marshall Space Flight Center. I'm sure Bill Lapenta has seen that before. But what I've been studying is the extreme hydroclimate implications of urban environments. How can cities themselves affect or enhance rainfall falling from the sky, and then in turn, how does the impervious surface or urban land cover lead to increased flooding? And so that's what you see here. In fact, I was one of the co-authors on a recent National Academy of Science NRC report looking at urban meteorology and the challenges associated with it. I published a paper along with my colleague Karen Cito at Yale. You can't read any of this, but this is one of the, I consider the most sort of relevant papers to give you an understanding of all the various pathways that cities can impact weather and climate. And I'm most interested in clouds and precipitation. And so this is just a myriad of results from some of my papers and work over the years showing evidence that cities can enhance or even in some cases initiate rainfall or storms. Top left. What you see in red there is the pre-urbanization rainfall in Houston, Texas, as measured by a long-term ground-based rainfall data set. And you can see in blue the post-urbanized radar rainfall data set in the warm season for that city. And so you can see that there's been a shift and an amplification of the rainfall totals there. On the bottom left is a warm season climatology of rainfall from radar data, Doppler radar. The dark green is where it rains a lot in Georgia in the warm season, climatologically averaged. What you see is it rains a lot in the mountains. We expect that. It rains a lot down in the coastal plain as sea breeze fronts move in. We expect that. But look around Atlanta. We get a lot of rain over the city of Atlanta and just downwind of Atlanta in the east. That is being caused in part, we found, by the processes associated with Atlanta. And then on the top right there is a figure from the TRIM precipitation radars, some work with Devna Yogi over India. And basically you see that little difference in the two lines there in that graph. The line that's leading or out ahead is all of the urban pixels, rainfall over the urban pixels aggregated together. So there's a slight bump in the rainfall totals in the urban pixels on aggregate in India. So we clearly understand that urban environments are modifying rainfall. The hypothesis, I don't have, if this were a different talk at a different time, I'd go through in great detail the reasons why that can happen, but just know that it's related to the fact that cities are warmer, so there's destabilization, the air wants to rise. Secondly, we have a lot of buildings and surfaces in cities, so you get mechanical turbulence and convergence that lifts the air. That's an ingredient we need for rainfall. Thirdly, cities have a lot of pollution in them, aerosols, and that can actually have a reduction of rainfall or an increased effect depending on the circumstance. And at times, cities can actually bifurcate storms that are moving towards them. There's evidence in some of our papers and others that storms approach cities and actually bifurcate around them, either through a thermal response or a physical response. Still, the jury's out on that. This is some work from one of my recent papers with students. This is actually the red and green and the orange and red are rainfall totals aggregate over the warm season from 2002 to 2015 around the city of Atlanta, Georgia. And again, it just shows you what I showed you in that previous radar image as well. Over the city of Atlanta and immediately downwind, there's increased rainfall in the warm season. There's nothing climatologically different about the western side of Atlanta in this image or to the north or south. It's the same climate regime. But we see enhanced rainfall in the warm season for the reasons that I just talked about. So with that, I want to draw to a close. This is just a slide that acknowledges that much of the work that you've seen today, this legacy work, has been enabled by funding from the NASA PMM program and Dr. Ramesh Kakkar, and our new work on the Brown Ocean by Dr. David Considine there at NASA headquarters. And the point I want to make here as we move forward is knowledge is gained through sustained understanding and long-term observation. We've seen that with things like Landsat. We continue to see that with TRIM and now in the GPM era. And so it's important that we maintain a robust observation capability with our satellites, started from these legacy satellites that we're acknowledging today in the session. Thank you.
Next up is Susan Avery.
Well, I'm glad, Marshall, that you mentioned the ocean and your hydroclimate. Often the ocean is ignored when hydrologists talk about the water cycle. In many ways, NASA and that first visual picture of our planet from space really, I think, drove home the immensity of the ocean that we have on this planet and the uniqueness of the planet from that ocean. And it's true that the ocean covers 2/3, oh, I gotta use this, right? Yeah. 2/3 of our planet's surface. But I think people don't realize also how important it is to our weather and climate, and how it averages on a depth of 2 kilometers Its deepest point would swallow Mount Everest with 2 kilometers to spare. It holds the longest mountain range on Earth, the highest waterfall, and the tallest mountain. And so when you strip that water off of the planet, which I just did here, you see that most of the water on our planet is contained in the ocean. The second largest dot there is all of the available, or the total fresh water. And then the tiny little dot, which has been overemphasized here, is the available fresh water. So you're looking at this, the dimensions that you see here, this visualization of what such a unique feature is to our planet and how it drives the life on this planet and the ecosystem services that it provides to humans and to other life on the planet. The problem is in getting and penetrating into Poseidon's world, the world of the ocean, you really are confronted with a lot of challenges. For example, it's much more difficult. Water is much more difficult, a medium to work in, than a gaseous form of water, the atmosphere. Water is very corrosive. The ocean is very corrosive. It's very salty. The pressures are unbelievable. I often say it's much easier. You only have to overcome 1 atmosphere to get into space versus the hundreds of atmospheres you need to get to the bottom of the ocean or to the seafloor. But most importantly, water in the ocean is largely opaque to light and radio waves, which is fundamentally how we observe the atmosphere. Okay? So the atmosphere is electromagnetic radiation, and the interaction of that electromagnetic radiation that allows us to make the tremendous measurements we've had from space of the atmosphere. Oops, no, that's not what I want. I've got to find out which way to go. Okay, but where satellites have really, really opened our eyes to the ocean is at this interface between the sea and the atmosphere. And this just is a depiction, if you will, of that interface, that connectivity, and all of the ways in which the ocean and the atmosphere communicate to each other. And the fundamental reason that the atmosphere matters to the ocean and the ocean to the atmosphere is that they exchange heat, moisture, momentum, nutrients, and biogeochemical properties. And so where the investment in satellites has really helped and advanced our understanding of the ocean is in looking at this interface between the ocean and the atmosphere in many ways, through radiometers, through scatterometers, through altimeters, and through a measure of color of the ocean to give us a measure of the biological productivity in the ocean. Is it this one here? Is it just? Okay. So I sat down and I tried to think. I talked with a lot of different people and said, what have satellites done for us in the ocean? I think the sort of general theme is that they've really advanced our ability to look at prediction and the interconnections that we've talked about so today. And here are just some of the major sort of talking points that came out of discussions, that the spatial and temporal scales of variability and its complexity from the vantage point of observing from space, look at that big piece of ocean and just being able to see that. Continuous observations over decades that has been committed to by NASA and European and Japanese colleagues as well. And we're really challenged to replicate what is seen and the challenge to assimilate that satellite data. Really, that visual sort of look and that data really challenged us as a community to think about our models and to think how to assimilate that data into those models. Mesoscale variability, eddies, what's happening in the Gulf Stream and the loop currents that so much drive in are very important for hurricane formation. Those tropical instability in the waves at that sea surface, very, very important. Most of the understanding of the structure of the meanders in the major currents that we see is largely derived from satellite observations. How the ocean shifts and changes, the spatial variability of these fluxes across the atmosphere-sea interface, the communication between the atmosphere and the ocean, the air-sea fluxes, the new products that are derived not only from satellites, but the combination of satellites and in situ sensors that basically have given us new looks and understanding of what the ocean is doing. And correspondingly, the advances that we've seen, not only in satellites, but also in situ sensors, have really enabled us to advance in the model development of the ocean. Okay, so just real quickly, these are just some slides of that I've picked through the literature. The altimetry and sea surface temperature allowed us to map the location and the variability of ring formation in the western boundary currents. The western boundary currents are basically the main currents that you see from a visualization. Discovered new recirculation gyres that are associated with the western boundary currents. And really, because of the long-term records that have been enabled, discover the interannual variability of current locations. And so what you basically have here is a figure that just shows the sea surface temperature and color and the values of the sea surface height deviation along a particular altimeter track. And that just basically is a visual of how the sea surface temperature and altimeter can show a structure in the rings and the meanders of this. In this case, it's the Gulf Stream itself. This actually emphasizes this a little bit more, but now looking at, again, the tropical cyclone heat potential, and the circles show the track and intensity for Hurricane Katrina that you see right here. And just think just how useful it is to discuss that the sea surface temperature and altimetry to help determine what that heat potential is, which is so incredibly important to hurricane formation and abatement. This, looking at, again, the structure, you think of this. I think when I first started looking at the ocean back in my early careers, many, many decades ago now, you were lucky to just talk about the meridional overturning circulation or the thermohaline circulation. Now we talk a lot about the eddy structure, the mesoscale eddies that are available from this high-resolution look from space using altimeters. And it really helps reveal the global existence of these eddies and thinking well beyond about, okay, how do these eddies basically, just very much like in the atmosphere, how do the smaller scale motions influence the larger scale motions and how that also impacts, in the case of the ocean, nutrient cycling as well. So it's sort of, the satellites have revealed the presence of these zonal fronts and jets that are everywhere in the ocean. They've positioned and strengthened the meandering of the jets that have been identified. And the interactions of these eddies with the mean flow has actually been investigated and revealed. And then again, from the satellite perspective, seeing this tight coupling between the ocean and atmosphere here, which you've seen right here. These are basically the color-coded currents and sea surface fronts and sea surface temperature on the winds. And you basically see that strong correlation between the atmosphere and the ocean from a satellite, from a space perspective of looking at our globe, our planet. But this is not sufficient in many ways. And in the future, what you're really seeing now happening, because of the solid year-to-year ability of getting satellite data, as well as the investment in situ measurements in the ocean, the ability now to develop complex data products that combine satellite data and in situ data is opening up a whole new world of looking at the ocean. This is just a work in progress here that is using the ocean sites profiling networks as anchor points for developing satellite-based air-sea fluxes. But just look at that resolution that you're beginning to see, both in the annual mean ocean surface heat uptake on the right-hand side, as well as on the left-hand side, the stress or the curl that's associated with it. This is what, of course, drives the winds and currents. There's one example that I'm awfully fond of, and it complements what Marshall has talked about in terms of looking at forecasting. And there's long been this sort of a group of people who's been really interested in, is there a connection between ocean salinity and terrestrial rainfall? And for those of you who don't know, most of the time you look at subseasonal and seasonal forecasts by looking at the surface of the temperature of the surface of the ocean. But this particular work that was done by Lee and Schmidt and Umenhofer and Karnauskas really started looking at the salinity and salinity changes in the ocean and how that might drive terrestrial rainfall on subseasonal and seasonal time scales. And this is actually shows that the salinity, which has come from the SPURS program, a really good program that NASA funded to look at salinity measurements that had a lot of ground in situ observations as well as satellite observations of salinity. And basically what shows you here is that evaporation at a certain point leaves the ocean saltier. That water vapor that is transported to, in this case, the southern United States. And when it comes into the southern United States, it builds up soil moisture. Okay? And that second panel, about 2 months afterwards, the moist soil draws heat from the sun at the beginning of spring and into summer, draws heat from the sun, warming and moistening the air above it. That warm, moist air rises. And what does that do? 3 months after the original loss of salt, as the rising air draws in the moist air from the Gulf of Mexico that heads north, increasing rainfall in the Midwest. So Aquarius and SMAT were measuring the salinity and soil moisture. Argo floats were measuring salinity and other variables during this campaign. And they actually went out on a limb and at an AMS meeting said to Minnesotans, you are going to have a wet summer because of this 3-month correlation and delay between patterns of salinity change and what that's going to expect it to do in the United States. And in fact, this was in 2015, and in fact, the Midwest did have a very, very wet summer. So when I look at my weather colleagues here and they talk about the weather bill, et cetera, I say, don't forget, if you're doing subseasonal and seasonal forecasting, you have to start thinking about the ocean. And Marshall's heard me say this many times. This is another fun little thing that just talks about how satellites help scientists answer questions about life in the ocean. And this is basically leatherback turtles. These are tracks, and you see this little turtle. So the turtles were basically tracked by Argo transmitters, and this is tracking on the circulation of the North Atlantic, circulation derived from satellite altimetry. And I hope what you saw is that little turtle just following the eddies that you could see in the satellite altimetry. Now, why is that so important? Well, there's always been a puzzle as to why turtles, particularly the leatherback turtles, but sea turtles in general, will pick certain beaches to hatch, okay? And it's because, in many ways, of this information that by certain beaches have certain eddy circulation patterns that allow the hatchlings to have a better chance of making it out to sea and surviving. And somehow they know that's what's going to happen. Of course, also these eddies basically also concentrate nutrient sources for the sea turtles as well. Got to have a little bit. Now, I've been talking mostly about the physical ocean environment, but the biological ocean environment is done with looking at ocean color. That's just basically intercepting the different color bands of the ocean, and those different color bands determine what's in the ocean. So again, there's been now multiple years, decades, of ocean color measurements that allows us to look at global trends in ocean phytoplankton. And this is a fairly recent article from Greg Rousseau in France, looking at the ocean plankton. And you're basically beginning to see, red means loss and blue means gain, but you're beginning to see declines in some of the critical pieces of phytoplankton in certain regions of the atmosphere. This assimilates data from 3 satellites over 17 years, and they're able to now really begin to detect some changes that are significant, that are not going to be available or obvious from just the imagery alone. Another one is looking at new satellite LIDARs that are breaking new ground on ecosystem research in the polar regions. The polar regions are it's difficult to get a look at the ecosystem of polar oceans because it's dark a lot of the time. So using LIDAR technologies has advanced our capabilities of looking there. Almost done here. Looking into the future, the marine boundary layer, one of the mysteries that we don't know a lot about. The idea that multiple satellites with multiple results give great knowledge for ocean sciences, integrating the data, looking at the whole Earth system responses. There's new sensors and techniques that are looking at that will help advance our measurement of the ocean. The CubeSat revolution is upon us. It's something to take advantage of. And there's obviously going to be real advances that are going to come in the future. And what I would like to leave you with is a picture, a visualization here of surface currents color-coded by sea surface temperature. This is basically a data assimilation of both ground-based data or in-situ data as well as satellite data with an eddy resolving model. And I think you can see, I hope it's out, the ocean does move much slower than the atmosphere. So it takes a while to get through, but just look at what you can see from this interface and this interconnectedness of the data streams that we do have, along with an eddy resolving model that allows us to capture these motions. And I would like to just add to Tom's comment. Right now, we have one data point, one ocean that we've really looked at. And the idea of exploring other oceans, particular Europa, which is shown on the left. On the right, you see on the left Earth with its, on the right, that's Earth with its water, on the left, the moon. And you're right, there is much more water sitting in on Europa underneath an icy shelf. And I would encourage, I think that's really important for ocean scientists to really get involved in looking at this new opportunity. I noticed that there is a nice lecture on ocean worlds at this conference, as well as Chris German, an oceanographer, who's really going to help lead off a session on how ocean scientists could be engaged in this ocean world exploration. So thank you.
Okay, there's no point, right? Okay, I can do it. Okay, so what I'd like to do today is talk about a tremendous evolution of science and technology that began early on with the Nimbus series of satellites going to the present day. And I want to in particular just talk about a few results from LIMS, HALO, SABRE, and the AIM satellite mission that I've been directly involved in. First off, I've listed here the missions that I'll be talking about. The Nimbus 7 mission launched in 1978 with the LIMS experiment. This was an exploratory mission. We knew very little about the stratosphere. It was exciting in that way, and there was really an explosion of information that started to develop, beginning with this Nimbus 7 mission. Then the Upper Atmosphere Research Satellite mission, which was launched in 1991 with HALO on board. It was a Earth science mission, as was the LIMS. And that was focused, in this case, on the ozone layer integrity, all about the questions about the effects of chlorine on ozone. And then another one I was involved in was a timed mission, which was launched in 2001 with the SABRE experiment that I'm involved in, and it's a heliophysics mission. And this was also exploratory, like the LIMS was, but in this case to explore what we call the ignorosphere, which no longer is true after 21 years or so, but it was a region of the atmosphere in the mesosphere and lower thermosphere that was not measured very much, no satellites, no in situ measurements, or very little. And then I'll end up with a slide or two on the AIM mission that was launched in 2007, also heliophysics in focus. It had two instruments. SIPS has two instruments, SIPS and SOFI, both SABRE and AIM are still operating. And it was an exploratory mission also, in this case, to study noctilucent clouds, what makes them form and vary. And then I didn't mention, but both in SABRE and AIM, I'll show some cases of where there's connection between earth science, helio, in both of these missions. So let me talk about LIMS now. LIMS, what I think ushered in really a new observational era. And it was the beginning of definition of the upper atmosphere, knowledge of the chemistry and dynamics of that region. And now that our knowledge has matured to a very advanced stage. And we started out with measuring in LIMS temperature, ozone, water vapor, nitrogen dioxide, and nitric acid. As I said, this was really nothing known about those gases in the atmosphere at that time. And it was therefore this mission, Nimbus 7 mission and LIMS, because Nimbus 7 had 8 other experiments on there doing other things. But this LIMS mission itself was groundbreaking in many ways. It was a broadband radiometer mission instrument. The signal to noise the goal was to have enough signal to noise to make useful measurements to make a big difference up to 65 kilometers altitude, and to have sufficient off-axis light rejection to be able to make the measurements with the noise that we had, and sufficient spectral out-of-band rejection. And then we had to have detector cryogenic cooling, and I'll just show a early drawing of the LIMS instrument, which you can see there. And I don't know whether you can see this very well, but this is I'm pointing out right here is a solid cryogen cooler. In those days, we didn't have refrigerators that we flew, so it was an ammonia methane ice box, basically, to cool the detectors, and it was needed. So there were 6 channels on LIMS. Mercury cadmium telluride detectors were cooled to 64 K, and it lasted for 6.5 months, and that was one of the great limitations, and spawned and encouraged the development of space refrigerators, which we now fly today routinely. So that was one of the big technological spin-offs from this mission. But in that 6.5 months period, we learned many things, and I show this one figure here, which is LIMS water vapor, monthly zonal mean water vapor for May of 1979. LIMS was launched in October of 78, went through May of 1979. And this was truly a groundbreaking figure that you're looking at the time, but there was so little known. Models were in their infancy, and we didn't know much at all about the upper atmosphere. So what we're showing here, on the ordinate here, this is 100 millibars, which is about 16 kilometers. And it goes up the top about a millibar, which is about 50 kilometers altitude. So that's the stratosphere is our main target. But notice in this zonal mean cross-section now, these light blue colors are water vapor on the order of a few parts per million by volume. And then you see up in this region here that the transport of water can't do that very well, so I'll just kind of talk to it. Transport of water to the high latitudes in the summer hemisphere, and some attempt at of the atmosphere for the winter hemisphere. This, this diagram, this figure that we're looking at, just really changed the way we were thinking about water vapor. There was estimates or measurements actually going anywhere from a few parts per million as the, quote, stratospheric water vapor to as much as 14 parts per million by volume, which is the stratospheric water vapor. In the former case, it was because the measurements were all looking at this hydropause, just this low value of water just above the tropopause in the tropics. And because we didn't have the whole picture, so we didn't know otherwise. And then for the 14 parts per million, that was occurring because there was water being carried up with a balloon. So, and then they were measuring the excess water from the balloon. So this is the first time the picture got clarified. Very exciting result. Another exciting result from LIMS is this NO2 zonal mean cross-section for January 5 through 9 of 1979. And this is going from at the bottom 16 kilometers up to about 65 kilometers at the top. And in this area right here where you can see the NO2 going with latitude, it drops off very precipitously right around 45 degrees and goes essentially away. And this is a so-called Noxon cliff that John Noxon spent much of his life trying to understand and make progress in doing that. But up here is what I really wanted to point out, which is the first measurements of NO2 in the polar night, and the first measurements of this vertical descent of nitric oxide reacting with ozone, forming NO2 with nothing to destroy it in the night and creating the excess there. And that was also exciting and groundbreaking. Well, going from number 7 to the Upper Atmosphere Research Satellite, there's a lot of years in there. 1978, number 7 was launched. URS was launched in 1991 in September. And in that intervening period, models became very active, started to become advanced. There was Nobel Prizes won by Mario Molina, Sherwood Rowland, and Paul Crutzen. Those three were doing groundbreaking research on what could be causing changes in ozone. And while that was all going on, then we had the discovery of the ozone hole. This is by Joe Farman and others from the British Antarctic Survey. And then the number 7 instrument confirmed the existence of the hole, the total ozone monitoring system, and made measurements of the ozone hole up to 2002. So there came number 7 back into the picture. So in the case of URs, it was all about the effect of chlorines on ozone. And I had the experiment called HALO, Halogen Occultation Experiment, which is focused on that problem. And so HALO was launched in what I call the environmental era. It's the first time where we were driven by models, by actual data now in the case of the Farman information and expeditions to the Antarctic, that there was a hole in the ozone, and it was being potentially caused by things that humans are doing. And so with that, armed with that kind of information, URS was conceived and developed, and then HALO was one of those missions. And it was all driven, the technology now started to evolve. We needed very high spectral resolution in order to make those kinds of measurements. And of course, high signal to noise. So HALO had that using gas filter correlation radiometry. In addition, there were other experiments on URs. The MLS instrument used very high spectral sub-line width resolution, and also clays. And then finally, the detectors, in this case, since we were looking at the sun, we only needed thermoelectric cooling, not a refrigerator, at least not a very strong one. So it was all about these two molecules really looking for the chlorine problem, HCl, and it's had natural sources and human-induced sources. CFCs were the human-induced, natural was the methyl chloride primarily. And then HF, the other molecule HALO was measuring, had only the anthropogenic source embedded in the CF2, CL2, or the Freon 12 and 11. So just to show you one result from this, and this is at the top is a panel of mixing ratio in HCl on the ordinate axis, and it's true for all three panels, versus time in years, 1985 at the bottom, going on out to 2000. And at the bottom is the measurements of total organic chlorine from the 8-gauge network, in situ measurements that were made. And then in the middle panel is the measurements from the Jungfraujoch by Mayhew of HCl plus chlorine nitrate. And then at the top is the halo measurements. And here at the very top is MLS measurements from the R satellite, which is the first time it had measured HCl. And it was an offset there, but that was later resolved in terms of merging data sets. But the thing I just want to point out is that was a major step, because once you see the chlorine here start to drop off, it's pretty clear that something's happened to the input of chlorine in the atmosphere. And also, just to point out, at the ground you see where the peak occurs in an earlier year than it does in the integrated column from Jungfraujoch, and also earlier than that from the measurements of that Halo made of HCl. So this slide was provided to me by Nathaniel Livesey. It's an ozone anomaly, which is a difference about the annual mean every year from 1980 to 2015. It included measurements from Halo, SAGE, MLS, ACE, and other ground-based measurements. And what you see here is that as time goes on, you come to a point where the ozone anomaly is diminishing, and then it starts to level off in this region and then starts to recover again. So ozone stops to decrease around this time period right here, around 1995. And considering the age of air is about the time it should stop, based on the measurements that I showed you of total chlorine in the atmosphere. Just one other point about technology and what it's doing. What I'm showing here is on the left is a Halo instrument. It's a big instrument, 100 kilograms, 93 centimeters height. And now we have, with the technology that's affecting an instrument incubator program within NASA, those same measurements Halo made can be made with like a maximum 28 centimeter height, 30 kilograms mass, all because of advanced technology that's been spawned based on the need to continue measurements like this. So now I'll turn to the standard of the atmosphere using broadband emission radiometry, or SABRE. This is one of 4 instruments on the TIME satellite. It's a 10-channel infrared limb sounder. It goes from tropopause to 110 kilometers altitude. It was launched on December the 7th in 2001. We're now in the 15th year of data collection. We'll begin the 16th year in January. The instrument's working perfectly, the spacecraft is working perfectly. And it's to study the energetics and the chemistry and dynamics of this region of the atmosphere. This is a crossover mission in the sense that SABRE makes measurements of temperature, water, ozone, other parameters used for dynamics and chemistry, and also solar effects in the atmosphere. And it not only measures those things, but it measures the temperature, ozone, and water down to about the tropopause, up to on the order of 110 kilometers or so. And in addition to that, it's been used and shows connections between atmospheric regions, which I will talk about. So this is broadband radiometry, but it was more than LIMS. We had to now increase capability to get to higher altitudes, get higher signal to noise was needed. We needed higher off-axis light rejection than we did with LIMS because of the fact that we're getting better signal to noise, and therefore we can see the signal now, and we need to get rid of those other effects. We needed strong spectral out-of-band rejection, and we had, of course, in this case, active cryogenic cooling, which has been working again for this 15 years that we've been up. I'll show two results from SABRE. One SABRE result I'm showing is lower thermospheric CO2 distribution, which led to the discovery of a reverse circulation in the lower thermosphere, this region right in here. Circulation from the winter pole to the summer pole. That's why we call it a reverse circulation. You can see it in the CO2 cross-section, this region right in here where the CO2 contours are bulging up, and then over here they're bulging down, and that's giving you the circulation in that region. By incorporating that circulation into the TIE GCM model, the comparison with satellite data, for example, the GUVI instrument on the time satellite, the O-to-N2 ratio, caused a dramatic difference in agreement between the model and the data once that was added. The other thing I wanted to mention from SABRE, just to show you the variety of things that we're doing with it, this is the thermospheric climate index for CO2 in this case, and it shows that the solar cycle 24 is very different than the other prior solar cycles in terms of the total integrated power. And I show here in this plot a picture of a time series of the integrated power from the CO2 cooling in the atmosphere measured by SABRE. This was developed by Marty Malinzak, who is associate PI on the SABRE team. And what was done is in the early part of the time series, right in here, a multiple linear regression was used against the solar parameters, the AP index, the F10.7, and the DST fluxes. And then that was allowed and that reproduced the time series very well there, and we could go back in time. So what we see here is, first off, at the minimum, you can see this area right in here, that's very constant over all these solar cycles from starting with 19. But the integrated power, which is not varying very much over all these solar cycles, it appears to be very different than what's going to happen in solar cycle 24. You need a lot more years than what we're seeing to come close to matching those. So it looks like it'll be a deep solar minimum. So I'll just briefly mention this, which is technology development here, where SABRE now, with the same capability, can be produced with 1/3 can be made to make measurements of half the mass, half the power, and 1/3 the volume because of advances in radiometric technology. So the last thing I'll talk about is AIM satellite, just a couple of slides. That stands for Iranian Device in the Mesosphere. It's a SMEX mission. I show two things at the top. AIM is measuring polar mesospheric clouds. There's an imager on board. It measures polar mesospheric clouds with very high spatial resolution, 2,000 by 2,000 pixels. And then here at 50 kilometers, we measure with AIM looking at radiance, Rayleigh albedo anomaly. We can get gravity wave information. Here's an island in the Pacific, and you can see the wave structure there. And then we have also SOFI instrument on the AIM satellite, which measures temperatures, polar mesospheric clouds, water, methane, NO, ozone, CO2, and also aerosols and cosmic smoke. Well, here the technology changes were very, very different than what I mentioned before, but it's certainly being driven. The large array operating 265 nanometers, high signal to noise to get enough sensitivity to get very good measurements of the gravity waves that SIP showed. Special lens technology to be able to do the job that we needed to do with the geometry we were working with. And then SOFI, and I'll just mention one of its qualities, was transmission noise up to 1 part in 10 to the 5th, so very high noise to be able to make excellent measurements of the PMCs. So I'll just show one example of a result from AIM. It's a crossover in the sense of going from helio to earth science. So what I show here is a MET-up-A by IASI measurement of a storm in the troposphere. The effects of the gravity waves from the storm, you see the concentric circles right here, measured by ARIS on the Aqua mission. And then up at the top, the SIP's polar mesospheric clouds, which you can't see it too well, but you can see right in that region there, the curvature of the concentric gravity waves that made their way to 84 or 83 kilometers altitude. So just to conclude and to say that this NIMBUS program I didn't say anything about, but it was visionary and laid the groundwork for this advanced systems that we have today. And truly we stand on the shoulders of those who've gone before us, because all of this is built over the years, and a progression has occurred from going from LIMS to AIM in a major way. And I didn't mention MLS, of course, on the ARA satellite, but MLS on UARS to MLS on ARA also was a great advance. and the science will continue to drive the technology. We haven't reached the end yet. So thank you very much.
All right, thanks. Before we do any audience questions, I'd like to give panelists and the co-organizers a chance to ask any questions, so especially Alcea or Harry or any of the other panelists, questions for each other.
Maybe I can start it off. So we've seen from each of your talks, and they were fantastic, a lot of fascinating advances and developments since Explorer 1. When we think about all that, one of the things you might want to do is extrapolate into the future. So what I wanted to do is to ask you to consider some of the influences that are coming up that might affect advances in the future and how you see things evolving. So some of those include things like the proliferation of Earth-observing satellites. I think we have the potential for many, many more that'll be on orbit in the future, especially with the miniaturization that's going on, and as well as the advances in the launch industry. Another one is Internet of Things. So now lots of devices have smarts and measurement capability. Is that useful to us? How do we harness it? How do you make it work with the satellite data? And then finally, technologies like artificial intelligence and how they play into handling the vast volumes of data that we can now create for science and operations. So it's for all the panelists.
So is this on? Can you hear me? Yep. Okay, Harry, so I'll go first. In terms of future observations that I think from a prediction capability, again, I think in terms of the modeling, tropospheric winds is something that we've been seeking for quite some time, and that's a technological challenge. But I do think if we were able to get those data and assimilate them, I think that would be a significant improvement in the quality of our guidance that's available. And also if we had the ability to get structures within the planetary boundary layer, temperature and moisture structures as well from space, that would be another, I think, significant advancement. So I'll just stop there and pass it on to my colleagues for their comments.
Well, I represent the precipitation community, and right now the sort of state-of-the-art approach is really a constellation-based approach for global precipitation, which is used in the weather, climate, and hydrological models. And I think we're technologically bound to a constellation-based approach for some time, but there is some pie-in-the-sky discussion amongst our colleagues about placing passive and active microwave sensors on geosynchronous satellites, and what that gains us is a current steering view of hurricanes and other weather systems at all times, and so we could be measuring precipitation rather than having to sort of piece together a measurement. On your idea about sort of small sats, CubeSats, and some systems, we're involved in a couple of efforts at my university, and I do see these as actually potentials for the future. I showed some Landsat imagery showing very deep, I'm sorry, I think that was actually thermal imagery from an aircraft, actually, probably the Atlas, the urban heat island. We're experimenting with some wearable technology and the use of batteries in our cell phones to measure ambient temperature, using wearable buttons or ambient devices such as our cell phones to measure external temperature, and that would be quite valuable, for example, for validation of sort of high resolution detail measurements of urban heat islands and building and street corridors and whatnot. So I can see that era coming very quickly.
Yeah, I do think that that there are tremendous technology revolution that's going on here. That Earth system science being one of them. And when you think about the types of data that one's going to collect, how one looks at this Earth system approach, you're going to have a much more need for data integration, data fusion of the planetary system, the planet as a whole. And constellations of small CubeSats offer unique opportunities. The real question I always ask is, do you use these but make a requirement that the data quality still must be there, and the data connectivity must be there. So I think that's also true from the National Weather Service, is that moving to different types of data mechanisms is certainly worthwhile and we're looking forward to, but you've got to make sure that the quality of the data is at least as good as what you have now, if not better. And the latency, and latency's there. Yeah.
Thomas, were you looking to say something? Or?
No, I was just trying to fire him up here.
Any other questions from the panelists or speakers for each other?
Okay.
El Sayed, did you have something?
So now that kind of the threshold to space has been reduced and more nations are able to get science instrumentation and satellites and as well as operational assets out into space, what role does international collaboration going to play in the next generation of discovery and operations?
So to me, one of the biggest innovations that actually came out of NASA is not just so much just the spacecraft, it's the open data policy. So for me, that is one that we should just be as proud of as kind of the stuff that's flying around. That's the why, by the way, of why we do the work. So for me, based on that, you know, and because of the standard that was set through that, I think there's a basis, that a foundation for international collaborations that actually is transforming already now and will transform in the future, kind of how we look at the Earth, just because how orbits work, right? Kind of if you build an orbit kind of in low Earth that, you know, you want to fly over, you know, New Orleans, you know, that will go elsewhere until it comes back to New Orleans, right? And so the meshing of data and pulling it together, like we're doing with Japanese assets, with European assets, and others hopefully to come, will really provide that dense, large N, if you want, network that brings us better transformative data. It will only work, or will work on the basis of that exchange, open exchange of data. And I just really think that's interesting. One of the, and also I think that's where I see kind of a lot of the promise. Now, once you do that, what the other challenge you walk into is that a lot of the methodology we're using right now kind of start fading, if you want. You know, basically what happens is, as you look at terabytes of data that are coming down from a variety of assets, kind of the next kind of the threshold there is really, you know, a technology threshold that we're, I think, at this moment in time, a number of amazingly smart people are thinking about, and good ideas are out there, but I think is a threshold that we can't see around the corner yet, right? So kind of, I'm very optimistic about the international collaborations, and I see increasing importance in it just because of the reasons that I provided. I also see challenges that relate both, of course, to the policy related sphere, but really a technology level, because kind of things don't scale linearly when you put data together.
Anyone else on the panel want to take that one on?
You covered it all.
You covered it well.
He covered it all.
Great, then I think we can open it up to the audience. There's a microphone there, so if anybody has a question for a particular panelist or the panel in general, fire away.
I'm Dave Jackson, a seismologist from UCLA. I wonder if there's some overriding questions that people have, or are there some hypotheses that are in doubt and need some kind of test in the way that the CFC and you know, upper atmosphere hole kind of posed an important focal point?
So from a computational fluid dynamic perspective, I think some of the things that we're seeing now with, like, again, I come back to the GOES, I think we're seeing things we've never seen before, and I think it's going to force us to look at some of the hypotheses that we formed, especially with, I think, you'll see some with hurricanes, and I think convection, for example. I think it may disprove some hypotheses and it may prove others. But again, you know, some of the things that I saw, concentric rings emanating out from the center of the hurricane, I think it's going to really pave the way forward for new hypotheses and discoveries.
Okay, Susan?
Yeah, I think you will, in many cases, in many ways, the ocean is still probably a frontier of this planet. And with the changing climate that we are seeing, it poses a lot of questions to what is going to happen to life forms in the ocean. I think also on the atmosphere side, it's a question of what's happening to the natural variability that we've known before. How is that going to change? The temperature gradients are changing. The forcing mechanisms of storm systems are going to be changing. So I think there's some really sort of surprises that they're still out there that we really haven't anticipated. But we should anticipate that there will be surprises that we need to address.
Yeah, I would actually, to follow up with that, one of the surprises that sort of came into the literature a few years ago in the atmospheric sciences climate field is this notion of Arctic amplification, which is that as we see warming Arctic regions, that essentially erodes or reduces the gradient, the difference between temperatures in the polar regions and the tropics. And when you do that, you get a more wavy jet stream as opposed to a strong, tight jet stream. If you sort of imagine pulling on a rope, if you're playing tug of war, and you release your grip some, the rope will sag. And so in terms of our jet stream patterns, that defines the strength of drought, storm systems, blizzards even. And so I think that's one that really is still coming into view, but still somewhat was a surprise, and I think still needs some refinement.
One other thing I would mention is really not the magnitude of the problems that my colleagues have just been discussing, but certainly one of the things that's very clear is that, and I mentioned it a little bit in my talk, that the atmosphere, the whole atmosphere is very connected. And we don't understand that very well right now, but we do have a lot of data that's now coming forth that's going to allow us to tie it all together. I saw a session on space weather and the economic impacts and how you got at that. And I think that kind of thing is going to also drive some of the research that we're doing.
Okay, do you have something else, Susan?
Just to follow up on that comment is that, you know, sometimes I get asked, what research do we not have right now that is going to really complete the climate picture? And what you're really talking about is very important. And I worry that we haven't really done, or we're going to lose the capability of understanding stratosphere-troposphere exchange, particularly in water vapor, and both from the understanding both the lower branch and the upper branch of the Breuer-Dobson circulation. And you know, we've had that measured by satellites before, and it's a really critical piece of that whole climate picture.
Just before we go off to the next question there, having mentioned stratotrope exchange and water vapor, Jim, do you want to say anything about water vapor tape recorder? Because I think your halo observations were so seminal for looking at the water vapor and how that transported between the troposphere and the stratosphere and how that changed over time.
Yeah, well certainly the water vapor from LIMS was dramatic. We are just about to the point of getting similar pictures for SABRE. To focus in on the point that Susan was talking about, you're going to need very high vertical resolution to get at the question of water vapor and effects on climate in the lower stratosphere, upper troposphere. And that's certainly an area where we're headed.
Okay, great. Next question.
Hi, I'm Emily Lakdawala from the Planetary Society. We're a space advocacy organization, and occasionally we lose a little track of the fact that Earth is also a planet that we should be studying. I'm wondering, are there currently or forthcoming gaps in our satellite vision on Earth, and is there a need for public advocacy to support future spacecraft, and if so, you know, in what direction do we need to support? What spacecraft are in danger?
Marshall?
Well, I would just say that in the last couple of years, there were sort of looming discussions about potential gaps in both our polar orbiting and our geosynchronous capabilities. There was kind of a huge outcry in that regard, particularly for operational-based satellites. And so in recent years, we've launched the GOES-16, GOES-R satellite, and we just recently launched the next generation polar orbiting satellite, which we call JPSS, which is sort of carries many of the instruments that actually feed the models that Bill was just talking about, so they're vital. I don't know if you mentioned this explicitly in your talk, Bill, but I think something like 80 to 90, maybe 90+% of data that's assimilated, fed into our computer forecast models come from satellite data sets. And so the GOES-16, GOES-R satellite, which Bill has said that he was amazed at, and I am too, is kind of the really flashy sort of satellite, car satellite, if you will. If you go to a car dealership, it's the one that catches your attention on the lot. But those JPSS satellites with those instruments that are providing detailed vertical profiles of moisture and temperature and other things that are being fed into the models, they're sort of that workhorse truck on the lot. May not catch your attention, but you need it. So I think that we have to maintain a vibrant and sustained JPSS and GOES program on the operational side. I think as far as forthcoming missions on the research side, I think many of us are here at this table and otherwise, and the managers at NASA are waiting for the decadal survey to come forth. The National Academy's decadal survey will be coming out actually supposedly, I guess, this month or so, and that will really define where we need to be moving or going in neurosciences around with our observation systems. And so that was what guided us in the past decade, and we expect that this year too, this decade as well.
Well said. Thank you.
Anybody else want to, Elsa, did you have?
Well, I think I'll bring up from space weather standpoint that there is going to be a need to follow on to the measurements that are made currently by research satellites and discover the NOAA Discover, NASA NOAA Discover spacecraft, and ensure that those measurements, the upstream measurements and the measurements of the solar explosions using the coronagraph are continued to protect our infrastructure in that way.
And I guess I would be remiss not to sort of remind people about, for NASA Earth Science in terms of future observations, the total solar radiance instrument to the International Space Station due to launch, I guess last I heard, Friday, GRACE follow-on in the spring, and ISAT-2 in, I guess, fall. So, lots more things to help extend records that we've had in the past for environmentally important things. Anyone else?
I just want to quickly add to that, and it'll be brief, because I know you're capturing this, Emily. The key in what Jack just said is we have to maintain and continue observations to establish and verify trends that we're seeing. For those that may be skeptical about climate, and it's a small percentage, but they are out there, in order to establish a trend, I like to use analogies if you haven't noticed, but if I need to understand if my son has a fever, I can't just all of a sudden break my thermometer in the house and stop taking his temperature measurement. I need to sustain measurements over time to establish that it exists. And so with rainfall observation, ocean observation, everything that you've heard up here, we need to advance our technology, of course, and we will continue to do that. But we also, with some fundamental measurements, we need continuity. And that's very important across the board.
Okay, another question.
Well, no, actually it's a comment, a follow-up to the previous question. My name is Molly Hardman. I'm with the University of Colorado. And I just want to mention that there is a big looming gap, and we actually have a session on that tomorrow afternoon, and that's in passive microwave sensors. We have a record from Simmer, starting with Simmer in 1978, through the present, a very rich history. We use it to track sea ice, snow cover, and we have aging satellites and nothing in the pipeline at this point in time. So just my 2 cents. Come and listen to our session if you're interested.
Yeah, I will say that there are, you know, I don't know if you know my colleague, Dr. Tom Mote at the University of Georgia, but he does work in that very area on sea ice, Greenland primarily, and he often talks about the need for passive microwave as well. But one of the things he does admit, though, is there are passive microwave sensors aboard things like the GPM satellite and other. Now, I don't know if the orbits are optimized for the needs that you all have, particularly in that case, probably not, given that you're looking at the Arctic. But he does acknowledge that there are some passive sensors out there that probably could be leveraged a bit more, but also acknowledges exactly what you just said too.
Right. Anything else from the audience or from the panels?
Throw in another question. So as we've heard about like new techniques and developments that were done over the last 60 years, but there's new ones in development right now that NASA's flying and others are flying. So what is being done or what can be done to accelerate kind of integrating these new discoveries or measurements into kind of the operational forecasts? You know, when we make these discoveries of for instance, the what you described of hurricanes over land, et cetera, how is that being incorporated into, as an example, into forecasts right now?
I think that one's for you, Bill, right?
Yes, yeah, I guess it is. So the question there, you know, so that's a hypothesis that needs to be tested, right? So it's intriguing. I want to talk to you more about that. But again, that's how, you know, those satellites don't necessarily have to be operational to be informative to the way that we look at things operationally. And then from a, you know, again, from a modeling perspective, again, it's just not all about modeling. It's how we use that information for scientific discoveries as well. So yeah, I'll just stop there.
And I think this is a nice opportunity to sort of, for those in the audience, and this is probably preaching to the choir, to understand the differences in partnership between NASA and NOAA, in that NOAA is an operational agency. They've got to get the forecast out. They've got to keep our models running. A program like NASA, like our brown ocean concept that you mentioned, that's a scientific hypothesis and capability that we're evaluating. And so NASA's program will allow us to sort of, using some of the available modeling and capabilities that NASA funds and operates. It allows us to evaluate that particular hypothesis and move that forward if it's robust into perhaps a research to operations transition, the various mechanisms that NASA has along with NOAA through the Joint Center for Satellite Data Assimilation and other research to operations capabilities. But the point I want to emphasize to some in the audience is that, because this question often comes up, what's NASA's role relative to NOAA's role in some of these things? And you know, NASA really, for example, I worked in the TRIM and GPM missions, tropical rainfall measuring and the GPM missions. If you don't know those missions, they both flew radars, precipitation radars, the world's first space-based precipitation radars. Now, for various reasons, NOAA likely, from a budget standpoint, might not have taken a chance on putting a precipitation radar in space. Turns out it's quite valuable for many operations, many applications, and for research as well. And so now that we understand that capability through the R&D arm, then it finds its way more into the RTO, or research to operations pathway. And there's also, I don't often want to forget, the operations to research pathway as well, which is emerging.
I think there's a number of examples, right, of successful transitions. There's many, many failed transitions. Yeah. And what you learn from that is that a transition into operation is not primarily a technological thing. It's a cultural transition, right? It's kind of from willing partners that have to lock arms in the middle there somewhere, in which both of them are uncomfortable, and create a transition. And so for me, you know, kind of one of the most the principal reasons for transitions to happen is the desire of all parties to actually go in that direction, and that is, you know, like at various times different parties feel differently. I mean, just over time, and so basically. Part of that is that element, which is unfortunately in the social sciences more, the policy realm in some other reasons, in some other aspects, but is not primarily a technological type of transition. If it was just technology, it would be a lot easier.
Great point. Great point.
All right, we're getting close to the time that we're supposed to end. I guess, does anybody on the panel have any last comments that they would like to make?
Thanks.
Harry, will you just Did you want to say something, or you're just moving the microphone? Okay. All right. Well, then, I think what I would like to do is to thank the co-organizers, thank the panelists, and also to thank the AGU for giving us the opportunity to share this with you. I hope you found this useful. And I think 6 o'clock, it's time for us to let you go to the next session.
Thank you.